Beam Accelerator Facility is a new laboratory for basic nuclear physics research. At CEBAF, scientists can advance our understanding of matter itself by probing the quarks and gluons in the atom's nucleus with beams of electrons from a superconducting accelerator. CEBAF has an educational mission as well. The CEBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CEBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed. Tonight's presentation, the 16th in our series, is called Magnets and Their Attractions for Technology.
Welcome to the last presentation in the fall 1991 CEBAF Science Series. I'm Steve Corneliuson. I hope you've enjoyed this fall's presentations and that you'll continue enjoying them tonight. And moreover, I hope that you'll want to come back in the winter and spring for the lineup of presentations we have then, outlined on this flyer available in the lobby. For those of you who haven't been here, you may not know what CEBAF is. CEBAF is a new laboratory where scientists from across the country and around the world will come to learn more about the nucleus of the atom, learn more about matter itself. In order to do that, we're building a big accelerator in a tunnel underground, 7/8 of a mile around. And in that tunnel, there are arcs at two ends. In those arcs, there are about 2,000 magnets. And the magnet's purpose is to move the beam from side to side in the accelerator so that the beam can continue to be accelerated. Tonight's presenter is the head of CEBAF's ARCS department, Dr. Leigh Harwood. And what he'll be doing tonight is letting you learn more about and see for yourself the magnets in our accelerator, and also about a good deal more. So please help me welcome him.
I was just playing with some magnets. This is a new version of something a lot of us may have had as kids. It's a neat little thing. It's got some iron filings in it, and the front's magnetized, and you can erase it. Could anybody tell who I was drawing a picture of? The title of my talk, I use a little academic license and change the title to Magnets and You, Today and Tomorrow. I'm Leigh Harwood, and this evening I'm going to be assisted by Jeff Karn. Stand up, Igor.
I'm here, boss. I'm here.
And we'll start out with telling you a little bit about what magnets are, how do we make them, how are they used, and I think you may be surprised how pervasive magnets are in your life, and then where we're going with magnets in the future. Let's start at the beginning. The interaction of charged particles. The basic interaction between charged particles is the Coulomb force. You've got one charge here, one charge there. There's a Coulomb force between them. If those particles are moving, a relativistic effect changes that Coulomb force into a magnetic effect. So the magnetic effect only occurs between currents, not between charges, because if they're stationary, it's not magnetic. You get magnetic forces between moving charges, therefore currents. Now, that relationship between the electric magnetic field is here. Come on, groan, groan. Good, 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 good. Now, thank you. I feel like a real lecturer now. These are only equations I'm going to show you. I have to do homage to a gentleman named James Clerk Maxwell. He was the one that put all these equations together in the 1800s. He contributed a great deal to the area of physics, but that relativistic change in the electrostatic force has some properties about it. The force on a charged particle is first proportional to the field strength. Second, it's proportional to the particle's velocity. It's also proportional to the particle's charge. And the odd thing about it is that it's always perpendicular to the velocity of the particle. In other words, a magnetic force will only turn a particle. Therefore, it can never impart energy to it. Now, those are the words. Here's a picture version of it. We've got a small magnet here, a vertical magnetic field. The original direction of the particle is along the yellow line, straight ahead. But with the magnetic field in place, the particles are bent to the side. Now, as you can see, the high energy particles are not bent as much. That's a reflection of the fact that the higher the energy of the particle, the less the force is. So this is the fundamental picture of essentially all the magnetic effects that we'll see. Now, just if all we had was currents, we wouldn't be able to make very strong magnets. It's important that for us to build effective magnets, that we be able to enhance those fields. And it's done by a process called magnetization. Now, I'm going to take you down to the atomic level. We've got at the top a small atom with a nucleus and a couple of electrons orbiting around it. Now, those circulating electrons form a current. So there's an equivalent current orbiting that nucleus. That loop of equivalent current looks to the outside world as if it's a small magnet. At the top, we've got a picture of what all those little magnets look like if there's no magnetic field imposed on the material. They're just sort of randomly scattered around. Some up, some down, some sideways, some left, some right. But if we turn a magnetic field on, they start orienting in a particular direction, that is, along the field. Now, the drawing isn't mistaken in that some of those arrows are turned sideways. That's what happens in real life. How much this effect occurs depends on the material. Fortunately for us, one of the materials that has this effect the strongest is iron. The reason it's fortunate is because iron is cheap, and that makes magnets inexpensive to build. And to show you the kind of effect that that can have on the magnetic field, we're going to put a magnet together for you down here and show you the enhancement that we get. Here we've got some conductor. A couple of hundred turns of copper wire. Here we've got a sensor that will tell us how much magnetic field there is near this probe. If we can get a shot of the meter, this is a readout in a unit called Gauss, named for another famous physicist. There's famous physicists all through physics. Now, if you'd please turn on the power supply, and we'll see that the, whoops. Thank you. Okay. Now, the original number was from the Earth's magnetic field, about 1.5 Gauss. Now, we've got the power supply on, and we've got much more. Do you think you can put the magnet together, or shall we get somebody to help you? I'm a lazy devil. Okay. Outstanding. Okay, what are we going to do? We're going to add some iron to this, and we'll show you how much it enhances the field. Yeah. Okay, first, we've got a small piece of iron. First, they'll just slip into the coil. Just drop it in. Drop it in the hole. Bingo. A little bit of gain, but not a whole lot. The main thing, what we have to do is get that field moved out, and that's what we're going to use the steel for. Okay, let's add the top and bottom pieces. Okay? I'm going to lift that coil for him.
Watch that, don't fall out.
Okay.
Is that right?
Okay.
Hold that up right there so it doesn't drop. I think I better turn the car on.
Okay. Now the cute thing is the in order to put this together, we've got to turn the power supply off because the fields are sufficiently strong. We can't move the pieces of steel around now. And we're not going to cheat. All he did was flip one knob. We'll bring it back to the same setting. Okay, now we put it back in and bring the power supply back. So we've gone from we started at about 50 Gauss, and now we're up to 300 Gauss. Pardon? Oh. You got the meter back? Yeah. So we're up to 300. So, and all we did was add about $10 worth of iron. That coil cost $100. So we're getting a lot of effect and a lot of help from the iron. Thank you, sir. Igor. The other fundamental effect is, or the basic interaction between the currents, again, is, like I said, we started with the forces always being perpendicular, and it's between currents. And here I'm illustrating what two wires will do to each other. On the left, we've got the currents flowing parallel in these wires, and the force pulls them together. If the currents flow in opposite directions, they'll force them apart. Now, how we'll use that eventually is in things like motors, and the reverse will be used in generators. Motors and generators form part of the basic things that make our high-tech lives possible. Why are generators so important? We've got lights. The power for these lights are coming from generators, either over at Surrey or Yorktown, at some power generation station. But those are very large generators. We can do some very small things to illustrate how those work right here in this room. The principle that I'm going to illustrate is called Faraday's law of induction. If you remember the picture that I showed of a magnet with a wire, with the current going through it and being bent to the side, that can be, if you view it from a different perspective, that can be a wire. The charged particles passing through could be viewed as a wire moving through the field, and what that would do is force the conducting electrons along the length of the wire. And that's the principle under which all of the generators work. A wire moving through an electric field will induce a current. So what I'm going to show you, if we can get a shot of this scope. This is an oscilloscope, and what we're going to show here is we've got clip leads on the ends of this coil. This magnet is energized, and if I simply pass it through, you see that we generate voltage. Now, another way of doing it is to change the field in the magnet. So as we ramp the magnet up and down, the voltage generation changes from 0 to positive as we flip back to negative. So this basic principle is the wire moving through a conductor, a wire moving through a magnetic field is how generators work. But this is a little esoteric. I want some human power. And is there anybody that would like to generate a little electric power? What I've got are two little hand-operated generators. We'll see how much voltage these two gentlemen can produce. Huh? Let's hook that up. Okay. Now, all you got to do is hold it in one hand. Okay. Can you see? You got it on the camera? Okay. Crank. Okay, we're off scale. Okay, slow down. No. Other way. Okay. Try it again. You got a lot to beat here. Uh-oh. Connection. He's blowing so much current out, he threw the wire out. Try it again. Okay. So we got up to about here. So that's about 15 volts. Outstanding. Okay. Thank you, contestant 1. Contestant 2. Looks close to me, Jeff. Try again. Well, I guess we'll have to review it, have an instant replay after the seminar, and we'll issue a statement as to who the official winner was. But because the immediate reaction was, it's a tie, folks. Good. Appreciate it. Thank you. Like I said, motors and generators are essentially the reverse of each other. Where one, you move a wire through a magnetic field and produce current. In the other, you run current through wire in a magnetic field, and that makes the wire move. That'll then make the thing that the wire is attached to move. So you saw one of these producing field or voltage. You didn't connect that well, did you, Jeff? Work on it. Okay, let's try it again. Ah, there we go. Now, just to prove to you that we haven't cheated, we'll go the other way. So each of these, like I say, is a generator and a motor simultaneously. Thank you, Igor. He needed his battery charged anyway. Now, those are motors and generators. We you may not be aware of it, but your television, the center of a lot of our existences, rely on a magnet. Back there in the very back of the tube, there's a magnet that focuses that beam of electrons onto the screen. If we didn't have that magnet, that picture of me over there would be one great big glob. That's what keeps the electrons focused. Now, we've got a fair number of high school and junior high students here. I remember that the center of my existence at that point was pretty close to the stereo. That aside from my car and my girlfriend. The important part in a speaker is that's what makes it work. Here's a little picture. At the top, you see an artist rendition of a speaker cone. There's a piece of iron on the back of that speaker. There's a coil in the back of it, and if there's no current running through this coil, the iron is pushed over to one side. That's the rest position. If you then energize it, the iron is attracted to the coil. Here I've got a small speaker. Just to validate the drawing that I've got, here's the cone. Here's the magnet on the back. And here's the wires that we had to clip off when we ripped this thing out of Steve Corneliuson's pickup truck. But the oscillating voltage in this coil is what drives this cone to oscillate, that makes the air move, which we hear as music or a news report. Your microwave oven. I'm single. I do a lot of microwaving. So my life would be real difficult without magnets. Where is that magnet in the microwave oven? The thing called the magnetron that produces the microwave power has a magnet in it that is sweeping an electron beam to produce those microwaves. Transformers. We get power from the power stations at very high voltage. To make it useful, like these outlets have 110 volts, it comes from the power stations at up to 1/4 megavolt. We have to change that down to the lower voltages. So we use transformers. That's another example of Faraday's induction law. And then some things as simple as your doorbell. That's basically the same thing as a speaker. But instead of having a cone oscillating quickly, there's a hammer going ding, dong, ding, dong. There's some lower tech things in life. Magnets are used for lifting. If anybody works at the shipyard, I'm sure that you've seen large pieces of steel and iron lifted with large magnets on cranes. We also use magnets for holding. Got a few examples up here on the bulletin board, and you've probably got some examples on your refrigerator door at home. We also use it for sorting in a very similar way, in that we use a large magnet that is over a stream of material that's going by, like garbage. And we can sort out steel. We can also sort aluminum in the proper, if we've got the magnets in the proper configuration. Where's the steel coming from? Well, there's still a few steel cans that we have for canned vegetables and those kind of things. Another part of the Faraday induction law is that the aluminum cans, even though they're not magnetic, they do have current flowing through them. Those forces will drive the aluminum out to one side of the stream. So those are low tech, but they're fairly important for us getting along with our wonderful high-tech lives. But let's get on to really high-tech stuff. Having worked at charged particle accelerator laboratories for about 20 years, pardon me for having charged particle accelerators at the top of the list. But that's not just because I like them a lot. It's because I think they're very important for society. One is for basic research, and that's what we're doing here at CEBAF. The way that what? I'll bring it back. I'll bring it back. Chill out. I think someone's taking notes and is going to is working for extra credit. Okay. Now, how do we use a magnet in a charged particle accelerator? The fundamental idea is picture a magnetic field perpendicular to this picture. If we have an oscillating magnetic field or electric field between these two sides, we start the beam off here, it goes in, magnetic field bends it around, it comes across, goes around here. Now it gains energy again as it crosses this. It has a higher energy, it doesn't bend as much, it goes farther out, third time through, fourth time through, fifth time through. So we can keep accelerating through the same accelerating potential right here that we're driving from the outside. This principle was first used by Ernest Lawrence, and he's holding in his hand the world's first cyclotron. Right there. Essentially all of the accelerators that you see and hear about have really grown from that little thing sitting in his hand. A few other things that have grown from it are the nuclear weapons industry, but we won't go into that too much. Derivations of the cyclotron were used to separate the materials in the Manhattan Project in World War II. At CEBAF, As Steve said, we have 2 linear accelerators that we want to recirculate the beam through. And we do that, I knew I had a pointer, through these recirculation arcs. The straight sections are our linacs, made of superconducting radio frequency structures. We split the beam with magnets and then turn it 180 degrees and bring it back through. Now, not only, and after we've accelerated, we send it to the end stations for experiments. As Steve mentioned, we've got about 2,000 magnets to accomplish this with. But once we've accelerated the beam, we're not done with it yet, because we got to do experiments. This is a picture of the Hall C out here. It's on the site. It's 150 feet in diameter and has 2 spectrometers in it. This is a large dipole. And when I say large, I mean 500 tons. I would have brought it in, but we were afraid we'd mess up the nap of the carpet. Pardon? Yeah, well, I was just reminded that it would have been easier to take you out and let you crawl through it than bring it in here. These are additional magnets, and all of this is made possible without having to build a power station by a principle called superconductivity. And I'll get to the importance of that in just a minute, because it's far more important for another facility than for us. And that facility is a superconducting supercollider that they're building in Texas. That's a roughly, depending upon the phase of the moon, time of the year, roughly $8 billion dollar enterprise. It's 120 miles, 54 miles in circumference. Oh, okay. I was remembering it in kilometers. Thank you, Bev. And this is a picture of one of their dipoles. Now, at CEBAF, the magnets that we use look like this, or like this. Or if you take one of these and stretch it to be about 10 feet long, that's what we use to bend the beam. And has a field of about 6 kilogauss, or 12,000 times the Earth's magnetic field around here. At SSC, they're working at a much higher energy level, and they need much higher fields. In particular, they're working at 65 kilogauss. And what happens at those levels is steel doesn't do you any good anymore. The iron finally saturates and doesn't enhance the field anymore. So you need far, far, far more current to get the same field levels. If we had to do that with regular copper, it really would take several nuclear power plants to power that accelerator. But there are some materials that, when you take them to very low temperatures, near absolute zero, in particular, most of them operate at liquid helium temperature, they lose all electrical resistance. The resistance drops uniformly, and at a particular temperature, it drops to zero. Therefore, you can pack lots of conductor into, and lots of current into a small region. Now, a superconductor, a conductor the size of this pencil, can carry 1,000 amperes efficiently with no power loss. So you can have kilometers of coil without any loss. Without it, this is the size stuff you have to use to carry half that current, and you lose a lot of power with it. So the gain is orders of magnitude in effective strength because you can't use steel. Now, this is a cross section. The thing you have to pay is you've got to deal with all that liquid helium and then liquid nitrogen to shield the liquid helium. So here's the magnet. Right in there is where the beam is. All this other stuff is to keep it cold enough. And here it is with all the, not just the drawing, but real hardware. And to show you how important it is, I've got a drawing here of the SSC drawn on our local map. If it were made out of copper coiled magnets. With the superconductor, it's that size. A third of the cost is just digging the tunnel for this thing to go in. So if we had to make it this large, just building the concrete tunnel for it to go in would far dominate the cost of the project. And as it is, it's $8 billion. So it's quite important to have superconductivity. Oh, I know what I'm looking for. I promised those people to put that view graph back up. There are a few other applications besides doing nuclear and high energy physics with accelerators, and in particular, medical applications. Cancer therapy has been moved forward with accelerators. In particular, the project that I was a participant in at Michigan State, we developed a new, very small cyclotron for doing neutron therapy of soft tissue cancers. There's a program at Lawrence Berkeley Laboratory that was working on retinal tumors that had a 95% remission rate using a helium-3 beam from a 40-year-old cyclotron. So accelerators will affect you not only in the long term, but also, perhaps, let's hope not, in your own lives. Another way is for doing diagnoses. Radioisotopes are produced with cyclotrons. You make it a charged particle beam, that makes radioisotopes to do scanning. Has anyone had a thallium scan? No? Okay. If you go in for any of the radioisotope scans, those have probably been made with a cyclotron. Now, in the future, as well as having regular plain generators, we're hoping to have two other techniques available for large power production. One is fusion. Now, most of the power plants that you're aware of are fission plants where the atom is split, the nucleus is split. Well, if you take hydrogen and fuse it together to make helium, it's possible to get even higher energy outputs. One of the techniques for doing that uses very large magnets. The structure you see here is TFTR, Tokamak Fusion Test Reactor at Princeton. I have a helper, Igor too. Igor is lost. And the structure you see is basically a magnet. And to show you the scale, here are a couple of fellows on the side. That technology is a bit in the future. It's not cheap. We've put billions of dollars into it. It's going to take billions of dollars additionally to develop it. Another interesting technology that is already in a power grid is MHD, magnetic hydrodynamics. Who saw the movie Hunt for Red October? Great. There was a submarine in the movie called Red October. What was unusual about it? Made no noise. Propulsion system. They referred to it as a caterpillar or tractor drive. In point of fact, it was MHD. If you remember when the saboteur blew up one of the connections, the chief engineer on the Red October said, if it had been Scotty, he would have said, "Aye, Captain, we got crowd problems." That's because it's based on a superconducting magnet. And the way that MHD works is essentially the same as a generator, but as usual changed around a little bit, and I've got this changed a little bit. Now for power production, what you do is have a very hot gas, light from a regular power plant. And so instead of sending the gases up the flue, you send it through a channel with electrodes on the sides. So here are, if it's hot enough, you'll ionize the atoms in there so you have electrons and positive ions going through there. Now, if there's no magnetic field, this is what happens. It's just uniformly charged. You get no current flowing. On the other hand, if you've got a magnetic field, again perpendicular to the paper, what happens is the positive charges go in one direction, the negative charges go on the other. You connect those electrodes, and you get current flowing. One of these devices was built and is in service in the Moscow power grid. Don't get too nervous. We built the magnet. We meaning Argonne National Lab near Chicago. Now, the MHD drive that they were referring to in Red October, again, like a motor is the reverse of a generator, their drive was the reverse of this. They have a magnetic field, and they drive current in this direction, and that will drive what the current is flowing through, namely the water, perpendicular to it. So MHD is a possibility, is a small-scale reality for power generation, could be used for large-scale in the future, and could be used for powering real-life naval vessels. And one advantage, like was stated, it's very, very quiet. Now we've made a lot of energy. It's convenient to store energy. One of the things that power companies have to worry about is that when people wake up in the morning, they all turn on their showers so the hot water heaters come on. They turn on the coffee percolators. Starts going on in the summer around here. The air conditioners come on. So they have to have power plants to take that peak. Well, at night, 2 o'clock in the morning, those power plants are just sort of idling along, not doing much. So if they could produce power at a continuous rate and not have to have power plants for the peaks, they wouldn't need as many power plants. That would reduce the amount of pollution generated. That would also reduce our electric bills. Because one of the big things in our power bills is the cost of building new plants. One of the ideas for storing energy is to use large superconducting magnets. When I say large, I mean miles in diameter. You just pump the power in, and because there's no resistance, the current will just sit there and run for years and years and years until you want to tap it out. For materials research and chemical processing, special types of light are very advantageous. One of these things that's made possible by magnets in 2 ways are FELs. Those are free electron lasers. You may have seen the article in the local paper a few weeks ago about the project that we're working on here at CEBAF. The principle of a free electron laser is that you have magnets that vary in polarity from one location to the next that make the beam wiggle. You see, it's called a wiggler. The beam wiggles. And one of the odd things about charged particles when they wiggle is they give off light. And that's not just in this configuration. Anytime they bend, so anytime they're going through a magnetic field, they're giving off photons or light. By tuning the wavelength of this wiggle, you can make it give off a particular frequency by tuning that wiggle and then having some proper optical effects on the ends. And that will give you focused, coherent light, or a laser. And a free electron laser will produce high-power light in wavelengths that have not been available historically. Now, the lasers that you're used to thinking of are invisible lights. The two that we're planning here for CEBAF are infrared. So that's infrared is heat, essentially. And then ultraviolet. So one is on the low end of the visible spectrum. The other is on the high end of the visible spectrum. We're very excited about this because we'll be able to produce power levels of this kind of light that nobody else will be able to match. We have very strong interest from people like Xerox, DuPont, Bell Corporation, help me out, Igor, too, IBM, the small companies. They're interested in using the light and helping us build this facility. And they're interested in the long term in having lots of them. Similarly, synchrotron light sources. They produce a slightly different kind of light for slightly different purposes, but use essentially the same principle, but they don't produce coherent light like FELs. The last thing in high tech that I'd like to mention is MRI, magnetic resonance imaging. A few years ago, the very important development were CAT scans. Those use X-rays. They're a 3D X-ray, essentially. MRI is a magnetic system that can tell even more about what's going on in the middle of a living, breathing human being. You take a very large magnet, one that has a bore big enough to fit a human being into. You make it very uniform in field, and then pulse radio waves into it. By correlating where that radiation is scattered within the human body, because different materials, the hydrogen, the oxygen, the different things, will scatter this energy at slightly different frequencies of radio waves. You can tell what the different materials are, and by making slight variations in the field geometry, you can localize where exact field is, and the materials resonate or give off scatter the radio waves at a given frequency in a given magnetic field. So MRI would absolutely be impossible without magnets. It would also be virtually impossible without superconducting magnets, because all the systems that you see around, and they're getting pretty common now, use magnets that have the current put into them. They short the leads on the outside, and the current just runs. There's no power supply associated with them. Tell you what's going on in the future. Slight tilt to the world. Fusion isn't realized yet. We've got that to come. It holds great promise. It also holds great challenge developing it. Widespread use of MHD, either for power production or for propulsion, is to come. Very interesting development that's seen a lot of development in Japan and Europe is maglev, magnetic levitation trains. Instead of wheels, they have magnets underneath them. So you've got a car, magnets underneath it, and magnets on the bed. It moves without friction other than the air. Those could be very significant in the future, particularly for high-speed transit to replace aircraft. Probably the most interesting thing is a wider use of superconductivity. And the thing that makes that possible, now I'll go back to the one I put up too early, is that there are new materials being developed that do not need liquid helium to be superconducting. To make liquid helium, or to deal with the heat that's generated at those liquid helium temperatures, it's very power costly. 1 watt at liquid helium temperatures takes a kilowatt or 1,000 watts of refrigeration capacity at room temperature. Another way to put it is the cost of liquid helium is about like good scotch. There are new materials that are superconducting at liquid nitrogen temperatures, about 70 degrees Kelvin. Nice thing about that is that liquid nitrogen costs about like milk. What can that do for us? With these kind of power costs for the refrigeration, we can talk about having superconducting generators, superconducting motors. And to make the system complete, they have been working for several years on superconducting power transmission lines. So superconductivity could be in things that perhaps are even in your home 20 years from now. One of the most exciting things that in the future, we may have materials that are superconducting at room temperature. 20 years ago, liquid nitrogen temperature materials were thought impossible. People say now, gee, it's going to be really hard. They don't say impossible anymore that it'll be room temperature. It's simply going to take work. I can make a superconductor while we sit here. You sit here, I'll stand. This is a sample of the material that is superconducting at liquid nitrogen temperatures. This is a little small magnet. What I'm going to do is show you what happens when we cool this material. Just so happens I've got a little liquid nitrogen. Now, rise. Rise. What's going to happen is that as it becomes superconducting, the material is going to force all the magnetic field lines out. And to do that, it's going to lift the magnet. It's floating. And let's see, do I have a piece of paper? If that doesn't prove, if the spinning doesn't prove to you that it's floating, look, ma, no hands. Well, yes, sir.
What's the force that's acting on it? The spin? It's just levitating.
Oh, the spin? That's when I took the tweezers and spun it.
Okay, you spun it.
I spun it. Yeah. And the fact that it kept spinning and spinning and spinning and spinning was because it was on the supported by the magnets. Well, that is going to be, as I said, one of the important, probably the most important thing for magnetic development in the future. It's materials research that will make new things possible, make it possible for us to have new devices or improve the devices that we have. Hopefully, people in here may be not by this demonstration necessarily, but inspired at some point to go into engineering, materials research, even physics. I'm a retrained physicist. To work in the areas that will develop the things that will make your life and my life better through the use of magnetism in the future. Thank you.